Hello everyone, this is Arindam Mitra from the Institute of Mathematical Sciences in India. Today I will talk about characterizing incompatibility through their Naimark extensions. My talk will be based on my papers which is written at the bottom. In left hand side this is me Arindam Mitra, in right hand side this is Shibashish Ghosh who is my advisor and Prabha Mandayam who is my co-advisor. This is the motivation for this talk. This is the plan for this talk. At first, we will talk about the motivation, then I will talk about the compatibility of PBMs, then I will discuss the characterization of compatibility for N POBMs, then I will talk about examples, then I will talk about quantification of incompatibility through Naimark extension, then I will talk about the efficiency condition for the compatibility for a pair of dichotomic observables, then I will summarize it and I will talk about future direction, then I will end my talk. So let's start. Naimark's theorem tells that any POBM can be realized as a PBM in higher dimension. This can be rewritten as equation 1. So thanks to POBM, any POBM is implementable in as a PBM on extended system. So a general Naimark extension can be written as equation 1 instead. There one can use direct sum instead of tensor product. So if we use tensor product in equation 1, I will call it canonical Naimark extension. So we know that a set of POBM is compatible if a joint observable exists. In this case, this joint observable is G. If you take the marginal, you will get the individual POBMs. Commutativity implies compatibility, but compatibility for POBM does not always imply commutativity. So there is no straightforward necessary and sufficient condition for compatibility in general. This makes the task of checking compatibility of a set of POBMs very difficult. This suggests us to look into this problem, which we will discuss. So for PBMs, compatibility and commutativity are equivalent. So this is theorem 1, and in this case, the joint observable is the Jordan product. So Beneducci derived a theorem for a pair of POBMs. So according to his theorem, a pair of POBM is compatible if and only if there exists a common commuting Naimark extension. We show that similar results hold for N POBMs. If we have N POBM that is compatible if and only if we find a common commuting pairwise Naimark extension. When we will call a common Naimark extension, it means that we have used a same ancilla state, suppose sigma A, to construct that Naimark extension. Now suppose BN isometry which extend a POBM effect to the projected in higher dimensional Hilbert space such that equation 3 holds. Now equation 4 will hold if and only if P is commuting with U. So in the proof of theorem 3, we have restricted ourselves into this kind of unitary which commutes with the projectors on the extended Hilbert space, and we show that still the if and only if condition in theorem 3 holds. This makes theorem 3 a strong statement. In this remark, we have said that from the proof of theorem 3 we got a statement, that is if we have a common commuting direct sum Naimark extensions, then a commuting common canonical Naimark extension also exists for any set of observables. So for the better understanding, you can look into our paper. So let's example 1. In this example 1, we have considered two spin up observed variables along along z direction and x direction. We know that these two measurements are not compatible, but look into the pz. Pz is a Naimark extension of sigma z with respect to any anisila state outer product 0 0, and pz is a Naimark extension of sigma x with respect to anisila 1 1. So there is a type of in the second equation that will be sorry no there is no typo. Okay, so yeah, so therefore we got that using different anisila, if we construct the Naimark extension for incompatible observed variable also, you will get a commuting Naimark extension. Therefore it is clear that commuting Naimark extension using different anisila does not guarantee compatibility. Let's look into the second example. Here we have considered three unsharp spin-half observed variables with unsharpness parameter lambda. It is known that these observed variables are compatible for lambda less than 1 by root 3. So pi jk is the joint observed variable. Using that we can construct matrices from A0 to A7. Using those matrices we can construct a isometry V tilde, and we can extend it to a unitary V, and using this unitary V we can get the Naimark extension of the joint observed variable, which is PIs. And if we take the marginal of those Naimark extension, we will get the commuting common Naimark extension of individual unsharp spin-half observed variables. So let's look into the example 3. This is very important example, and importance of it we will discuss at the end of the talk. So suppose we have two unsharp spin-half observed variables. We know that lambda for lambda less than 1 by root 2, these two pairs are compatible. I mean, these two observed variables are compatible. But let's look into the equation 16. So P1 is the Naimark extension of observed variable A. Similarly, if you look into the equation 17, Q1 is the Naimark extension of observed variable B. And these two Naimark extension will not commute for any lambda. Therefore, for a compatible observed variable also, there exists some non-commuting common Naimark extensions. So here we have said that one can quantify incompatibility via Naimark extensions. Suppose I have a set chi, and Naimark extension of that set, it is pi lambda. Suppose I have a incompatibility measure for pi lambda, which is f. F is 0 if pi lambda is compatible, otherwise f is a positive quantity. So we can extend this measure for POVMs, I mean for the set chi, using minimization over the Naimark extensions. Here clearly G chi is 0 if and only if the set chi is compatible. One measure Q pi for PVPNs has been discussed in our paper, which is written at the bottom. So this measure also can be extended for POVMs as above. So Q prime chi is 0 if and only if chi is compatible. Otherwise Q prime chi is a positive quantity. Now this is a specific Naimark extensions for a dichotomic observed variable. Construction of it has been explicitly shown in our paper, which is written at the bottom. For two dichotomic observed variables, Beneducci derived a sufficiency condition for compatibility. We have checked that this condition is not useful even for two unsharp MUBs for any unsharp parameter. So we have derived a similar sub-efficiency condition for compatibility for two dichotomic observables, where if gamma is equal to identity theorem 5 reduced to theorem 4. So theorem 5 is a specific generalization of theorem 4. Now using theorem 5 for spin-up observables, we got another sub-efficiency condition, and this sub-efficiency condition is very useful to construct the compatibility region. So let's check how this sub-efficiency condition is useful. We have two observables, sigma x and sigma y. If we take gamma to be e to the power I theta sigma z, then the equations in theorem 5 will reduce to equation 31. So this equation has to be satisfied if the unsharp version of sigma x and sigma y will be compatible according to the theorem 5. So in equation 31, you can see if we change theta, we can make the right hand side from 0 to 1. So we get equation 32. This is well known in compatibility region for sigma x and sigma y. So now we will talk. We will summarize our results. So we have shown the connection between commutativity of Naimark extension and compatibility of POVMs. We also shown that non-commutativity of a single common Naimark extension does not guarantee incompatibility. So therefore example 3 is important, because after example 3 one can ask a question that is there exist any characteristic set of common Naimark extensions such that commutativity or non-commutativity of that Naimark extensions in that set will guarantee compatibility or incompatibility of POVM in that set. For better understanding, you can look into our paper. So we also obtained a sufficiency condition for two dichotomic observables, and we also got a sufficiency condition for compatibility for two spin-up observables, and we have seen that the specific Naimark extensions and through which using which we got the theorem 4 and theorem 5 and theorem 6. This Naimark extension is very useful because this sufficiency condition is giving us the full compatibility region for MUBs, and it is also possible that this theorem 5 can capture full compatibility region for any pair of spin-up observable, not just MUBs. And construction of such sufficiency condition for higher number of observables and in higher dimension with many outcomes is another important direction for further research. Thank you very much.